In this project, we are explaining the overall manufacturing process that is related to the laser dinging.
Our team is made of 4 group members. This is me, Hwei, then Zhen, Zhen, and NAUFAL.
Ding Searing is a small board with a single mass. It's built from a mill cell, heart, bone, and also the mass. Each part has its own specific role. The mass and bin are used to support the cell. The heart is the watertight body of the board, and the mill cell is used the wind power to propel the board. We will go over the steps involved in manufacturing process, beginning with the material selection and moving on manufacture. We separate it into 4 sections: the heart, cell, pulley, and mass and beam. For the production of the laser dinging, batch production and job production is suitable. Since laser dinging are frequently used for racing, customers may want to customize their board to their needs and specification, while batch production is suitable for manufacturing laser dinging parts such as bone, mass, and pulley, since they are already standardized. Firstly, the assumption is that the production volume must be aligned with the marketing demand, ensuring that sailboats are manufactured in quantities that meet or exceed the customer needs. Besides that, the research and analysis of the market play a vital role in forecasting the potential demand for different types of sailboats, ranging from high-end custom models to more standardized mass production units.
The boom and mast serve as essential components supporting the seal of the sealing dinghy. Positioned at the foresail base, the boom facilitates control over the seal angle and shape. The mast, a vertically resting pole, is divided into upper and lower sections, with the lower mast directly fixed to a dinghy hull. The lower mast design incorporates a hollow part for connecting to the upper mast via a T-junction. T-junction connecting is used to drain the boom and mast. Mast and boom are crucial for sealing vessels, with material selection impacting performance. Common mast materials include wood, carbon fiber, and aluminum. Wooden masts, rare in modern laser dinghies, are chosen for their classic appearance, but require more maintenance and lack the advantage of modern material, typically reserved for vintage or classic restoration. Next, the carbon fiber mast. Carbon fiber mast with a superior strength to weight ratio, enhanced agility and speed, referred to by racing enthusiasts. However, they come at a higher cost than aluminum, and their rigidity may require more precise training. Lastly, the aluminum mast. Aluminum mast provide sufficient and stiffness for most sealing, are cost-effective, and are corrosion resistant, making them suitable for saltwater environments. They are widely used in laser dinghies. Aluminum is resistant to corrosion, while heavier, it is dependable and suitable for most sealing applications. In simplest terms, an aluminum mast strikes a good balance between performance and affordability, making it a great choice for car racing and skill improvement. Metal forming processes like rolling, rodging, and casting are considered for manufacturing masts in sailing vessels. The selection aims to balance efficiency, customization, and structural integrity in the manufacturing process. Firstly, the metal forming rolling. Rolling is a widely used of metal forming process, providing high production and control. It involves passing metal between rollers to plastically deform it. This process is suitable for shaping aluminum beams, offering efficiency and control. Next, the metal forming forging. Forging involving hammering or pressing metal with fine-grained structure and enhanced physical properties. Forging is cost-effective and suitable for producing mass in dinghy sailboats, contributing to high strength, controlled gain structure, and minimal waste. Lastly, the metal casting, permanent mold. Casting, an alternative method, involves molten metal flowing into a mold. Permanent mold casting is considered for mass production, but may incur highly expenses due to its complexity compared to other methods. The chosen manufacturing process for mass and beam production in dinghy sealing board is metal forming, and specifically rolling. This decision is driven by multiple factors. Firstly, rolling significantly enhances the quality and mechanical properties of metal. It refining grain structure, increasing strength and hardness, and maintaining tight tolerance for precise dimensional control. This process allows adjustment of mechanical quality like tensile and yield strength to meet specific application demands. Additionally, rolling reduces residual stress, enhances material density and homogeneity, and improves surface finish, minimizing the risk of corrosion. Secondly, the cost-effectiveness and efficiency of rolling are evident as it minimizes material waste, enables precise sizing, and reduces the need for extra machining. Automated rolling mills increase production speed, ensuring a faster turnaround and reducing overall production costs. Finally, the automated and continuous nature of rolling enhances safety by requiring fewer manual intervention, minimizing the risk of defects that could compromise structural integrity, and ensuring constant product quality, contributing to a safer manufacturing environment for workers in dinghy sealing board component production. The manufacturing process for dinghy sealing board masts involves several key stages. In stage 1, a lightweight and corrosion-resistant metal, typically aluminum or similar alloy, is selected. Stage 2, entails cutting the metal sheet to the specified length based on mass requirement. Subsequently, in stage 3, the metal undergoes cold rolling through a machine with 2 rollers, allowing for shaping and thinning. Stage 4 involves strengthening to ensure alignment and dimensional accuracy. Bending, as highlighted in stage 5, is crucial for achieving the necessary curvature. The metal is then cut to the length again in stage 6 to meet design specification. Welding may be employed in stage 7 for connecting components if the design required. Following this, stage 8 involves finishing process like coating or polishing to enhance durability and appearance. Finally, in stage 9, the mast is assembled into the dinghy main structure, attaching it to other parts as needed.
The pulley block contains a wheel that is used to carry the rope, and the casing is hauled the wheel. The purpose of the pulley is to reduce the force required by the sail, which is used to control the shape and angle of the sail. The pulley block is fixed to the booms and the rope is connected to the sail. In the market, the material used for the pulley block are cast iron, alloy steel, and nylon. Grey cast iron has stronger under compression, excellent vibrational dampening, and wheel resistant. Although it is stiff and brittle under tension, the function of the pulley block is to withstand the load from the rope. Thus, strong compression for the pulley block is necessary for its performance. For the nylon, although it is a polymer, but it has high resistance to wheel, heat, and chemicals. High resistance to wheel is one of the considerable reasons for the pulley block. Low resistance to wheel requires the user to do replacements or service frequently. Besides, the pulley block that is installed for the laser dinghy is used for outdoor activity, especially on the sea. Thus, high resistance to the heat and chemical are major criteria for the pulley block. Cast iron, alloy steel, and nylon have their own characteristics and performance. The selection of materials for the pulley block also depends on manufacturing process. The final selection is alloy steel because it has high corrosion resistance, high temperature, and high tensile strength. Besides, its mechanical properties also can be improved through the metal forming process. Chromium molybdenum alloy steel has good mechanical properties which are corrosion resistant, high temperature, and tensile strength. This type of steel is suitable for the forging process that generate forged pulley. High corrosion resistance can prevent defect from the occurring on the ingot and final product. High temperature and tensile strength are allowing the chromium molybdenum steel to undergo a forging process. After undergoing forging process, the mechanical properties of this alloy steel are able to improve. There are several manufacturing processes that can generate the pulley, such as injection molding, forging, and casting. Basically, the forging process involves hammering or pressing a metal in a desired shape. Through the forging process, the mechanical properties of the product can be improved. The fibrous microstructure will be generated during forging, and it will have better mechanical properties in the plane of maximum strength. The injection molding process is used to produce the polymer pulley. It is accomplished by forcing the molten plastic into cavity between two matched metal mold halves. The injection molding process can produce intricate parts. Once the mold for the pulley shape is designed, it can produce the pulley at high production rate at low cost. The casting process allows the flow of molten metal by gravity, mechanical force, or hydraulic force into the mold, where it is solidified in the shape of mold cavity. This casting process is to produce the metal pulley. After consideration of mechanical properties, quality, weight, cost, production, and lifespan, the process for the pulley block will be cross-die forging. Next, I will continue with the process flow for the pulley block. First stage is raw material selection. We will select the material that was used for the pulley block. Second stage is hot rolling. This process is to break down the initial ingot into billet for further forging. Break down and heat the billet. This is the hot forging process. Heat the billet to reduce the stress required during the pressing process. The purpose of heating is to make sure the billet will deform and fit to the die cavity. The heating temperature should be above the recrystallization temperature of the metal. Next stage is install the die. The design of the die is defined as the desired shape and size for the pulley. The die material used should have high thermal shock resistance, high thermal fatigue resistance, high machinability, and high wear resistance. Medium alloy tool steel are typically used for the die material. The fourth stage is forging process. The heated billet is placed in between two die halves. Forging hammer fall down and apply huge compressive stress to deform the billet into the shape of the pulley. The metal flow and fill the die cavity. A flush will be formed. It is the excess metal that squared out from the cavity. So the next stage is trimming the die. Flesh is not one of the parts of the pulley, thus it needs to be cut by the trimming process. The sixth stage is heat treatment. The pulley is formed, but the mechanical properties have not specified the design. Thus, the heat treatment process is able to enhance the hardness and strength of the pulley. For example, the annealing process involves heating the pulley beyond its critical point where the austenite forms, soaking at a specific temperature and quenching in the oil. So the next stage is surface treatment. The black oxide coating is able to protect the pulley from the rust. It is chemical reaction that form an integral protective surface by using wax or oil. It is important to provide the protection against the corrosion. The next stage is Quality control. This process is important to check for the dimensional crack, hardness, and other defects that might occur on the pulley. Besides, the shape and size of the pulley are the part that need to be checked. So the last stage is packaging. The forged pulley is packed with its casing and the final product is formed.
Sail. Sail is made from fabric or other polymers. It is used to propel the sailing dinghy with wind power. It will be controlled by the boom and the pulley that connects with it. The sail will be supported by the boom and mast and fixed by using rope. The size and shape design are in accordance with the size of the boom and mast. The size is also following the standard laser dinghy. Due to the fair competition, the design and size are fixed by the International Laser Class Association. For the material selection, sails for sailing vessels are crucial components and their material selection plays a significant role in the boat's performance and durability. The common material used for sails are Dacron, Mylar and Kevlar. First one, Dacron. Dacron sails are a practical choice for laser dinghies, offering durability and affordability. They can withstand the rigors of training and recreational sailing, making them a solid option for beginners and those on a budget. Dacron sails are relatively easy to maintain and repair, which is valuable for novice sailors learning the ropes. Second one, Mylar. Mylar sails made from polyester film coated with resin are popular among competitive laser dinghy racers. They are lighter than Dacron sails and offer excellent shape retention, allowing for more precise sail control and performance optimization. Mylar sails are designed for racing conditions where every advantage counts. Last one, Kevlar. Kevlar sails are less common in laser dinghies due to their cost and specialized use. Kevlar sails provide the utmost in lightweight, strength, and performance. Kevlar sails are exceptionally durable and maintain their shape well, making them suitable for elite level racing in the laser class. However, their higher cost may deter the recreational sailors. Based on this material characteristic, we found that Mylar sails are the best choice. In terms of durability, Mylar sails are generally durable and resistant to UV degradation. This makes them suitable for long-term use and reduce the need for frequent replacement. Other than that, Mylar is lighter than Dacron and offers excellent shape retention, providing improved performance, especially in racing situations where sail shape is critical. Lastly, it is cost effective because the cost for Mylar is in the middle between the Dacron and Kevlar, which is affordable for everyone. For the process selection, there are a few alternative processes in making sail, such as traditional panel construction, molded sail technology, and laminate construction. The first one is traditional panel construction. This is more traditional method where sailmakers manually cut panels of sailcloth and stitch them together. The process begins with the sailmaker plotting the sail shape on the cloth, followed by the manual cutting. The panels are then carefully stitched together, often with reinforcement at critical stress point. This method allows for a high degree of craftsmanship and can be customized to the seller's preference. Although it might lack the precision of the modern methods, however, it is more labor-intensive and time-consuming, and there is a higher potential for variation between sails, which might not be an ideal in one design classes like the laser. Second one is molded sail technology. Since molded sails are made from a single piece of cloth without seam, they can offer better aerodynamic properties. This seamlessness can translate into smoother airflow and potentially better performance. The absence of seams and additional stitching materials can lead to a lighter sails, which is an advantage in racing conditions. The technology and equipment required for molded sails are typically more advanced and expensive, potentially making these sails less accessible for amateur sailors for small-scale operation. While molded sails can be lighter and more aerodynamically efficient, they might not always match the durability of traditionally stitched sails, especially in harsh sailing conditions. And the last one is laminate construction. Laminate construction in sail making is a modern technique that revolutionized traditional sail design by using multiple layers of different materials laminated together. This process begins with a base layer, often Mylar, a strong lightweight polyester film. Onto this high-stress fiber like Kevlar, Dacron, or carbon are placed strategically aligned along predicted load path of a sail. This alignment is crucial for handling the force exerted on the sail during use. These fibers are then laminated between additional layers of mylar or similar materials, sometimes using a mold to create a three-dimension shape from the outset. The process that we choose for the cell making process is laminate construction based on these three factors, that is quality and mechanical properties, cost and production rate, and safety. For quality and mechanical properties, laminate cell maintain the shape exceptionally well even under various wind conditions. This is due to the alignment of high strength fiber like Kevlar or carbon along the load path, which effectively handles the forces acting on the cell. These cells are lighter yet stronger than traditional cell. The use of advanced material provides a significant advantage in terms of performance, especially in racing. The combination of material in laminate cells offer reduced strength, allowing for more precise control and efficient wind handling. For cost and production rate, the advantage material like mylar and Kevlar and the lamination process used in laminate cells are more expensive than traditional cell making material. This results in a higher overall cost for the end product. Despite the higher material cost, the manufacturing process can be quite efficient. Modern technology allows for quick alignment and lamination of materials, which can partially offset the higher cost of material. Laminate construction offers the possibility for extensive customization, which can be both a cost-increasing and value-adding factor, depending on the requirement of the cell. For safety reasons, the consistent shape and handling of laminate cell contribute to safety, particularly in racing or challenging conditions. Sellers can rely on the cell's performance, which reduce the risk unexpected behavior in strong winds. Despite concern about long-term durability like UV sensitivity and potential for delamination, laminate cells are robust in the short term. They resist immediate wear and tear well, which is crucial for safety in demanding cell environment. For the process flow, there are many stages in processing the cells before the cells are ready to be sold. Cell design. The process begins with a detailed design, often using advanced computer software. This stage involves determining the cell's shape, size, and the specific load path, areas where the most stress is anticipated. Stage 2, material selection. The type of materials to be used like mylar, Kevlar, carbon fiber, and etc. are chosen based on their properties and the cell's intended use. Stage 3, cutting the fabrics. The base materials such as mylar or other films are cut into the required shapes. This is usually done with precision cutting tools for accuracy. Stage 4, preparing fiber. High-strength fiber are also prepared, which might involve cutting them to length or aligning them in specific orientation. Stage 5, placing fiber. The fiber are laid out on the base material. This placement is critical and is done according to the load path determined in the design phase. Stage 6, adding additional layers. If the design calls for it, additional layers of material may be added on top of the fiber. Stage 7, applying adhesive. An adhesive is applied to bond the layers together. In some process, the adhesive is already a part of one of the layers, like adhesive baked mylar. Stage 8, curing. The laminate is then cured, which might involve applying heat and pressure. This process solidifies the bond and gives the cell its initial flat shape. Stage 9, cutting and trimming. The laminated material is cut and trimmed to its final shape. Stage 10, adding hardware and reinforcement. Elements like batten pockets, corner reinforcement, and attachment point for ropes and pulley are added. Stage 11, quality control. The cells undergoes through inspection for any defects or deviation from the design. Stage 2, the last stage is packaging. The completed cell is folded or rolled, packaged, and prepared for shipment to customer or distributor.
A sailboat body is a floating bodies of a boat and create the shapes of the vessel. Without the body, there would be no boat. Sailboat body are wrapped around the flank of the boat and make out a significant portion of its structural strength. So let us discuss the bodies of the sailing boat. The selections of material for the body is very important. The first common material is aluminium. It offers an excellent strength to weight ratio, making the seal ball robust and lightweight. Besides, it is also resistant to corrosion, so requiring minimal maintenance. However, aluminium bolts may be more expensive to manufacture compared to other materials. Next, the material is wood. Wood gives a good visual for the sailboat, but it is required meticulous maintenance to prevent rust and deteriorations, and it is also heavy, which will impact the speed of the boat. Fiberglass is a composite material made from glass fiber embedded in a matrix of resins such as epoxy and polyester. It is lightweight, so provides a good strength to weight ratio. Furthermore, it has excellent corrosion resistance, making the body durable in the marine environments. It also provides a good balance of performance and cost. Based on these characteristics, the most suitable materials is fiberglass. For the manufacturing process for the sailboat body, there are several. The first one is the combinations of CNC cutting and aluminum welding. Basically, CNC cutting is for machining, while aluminum welding is for joining. In this method, the CNC machine will cut the aluminum plate. Then the body can be assembled by using aluminum welding. The advantages of this process are highly precise and allowed to make the complex shape. However, the disadvantages are require skilled labors and is very expensive. Second process is fiberglass reinforced plastic layout. It is a traditional method. The layers of the fiberglass fabrics are laid by hand onto the mold. Then the resin is manually applied to saturate and bond the fibers. The advantage of this process is high flexibility, while its disadvantages are labor-intensive, slow production rates, and waste generations. The last process is vacuum infusion. It is an integrated process for HRP layout. Basically, it has the same process as FRP layout, but it uses a computer-controlled machine. The advantages of this process are consistent quality and no waste generation, while the advantage is the high equipment cost for the initial setup. The process for a vacuum infusion is shown in the picture. There are a total of 10 stages. First stage is molding preparation. The mold is typically made of two halves. Second stage is dry fiber placement, placing the dry fibers fabrics inside the molds. Third stage is resin infusion setup, placing a vacuum base over the dry fibers. Fourth stage is resin mixing and reglassing. Mix the liquid resin with any required additive and reglass the resin mixture to remove air bubbles. Fifth stage is resin infusions. Introduce the liquid resin in the molds under the vacuum pressure. Next stage is curing. This stage will allow the resin to cool and harden. Seventh stage is vacuum release. Release the vacuum after the resin has fully cooled. Eighth stage is demolding. Carefully demold the sailboat body from the mold. Ninth stage is trimming and finishing. Trim the excess material and finish with sanding and polishing. The last stage is structural reinforcement, deck and rigging. It's necessary add structural reinforcements such as bulkheads and frames to enhance the strength. In conclusion, every part of the products have many kinds of material selections and manufacturing processes. The selected materials and process are the best selection after considering suitability, property, and cost. In this group project, we learn technical drawing skill, communication skill, commitments and cooperations between our group members. The contributions and each member is important for us to complete this coursework.